In this example, we will conduct a hypothesis test for a proportion. So the rate of brain cancer was commonly believed to be 34 thousandths of a percent in the general population. So this means that the proportion of individuals in the general population who developed brain cancer was 34 thousandths of a percent. Now, in the 1990s and 2000s, cell phone use became widespread. In a study of 420,019 randomly sampled cell phone users, 172 developed brain cancer. We're going to test the claim that cell phone users develop brain cancer at a rate that is higher than the general population, so a higher proportion of them. We're going to use a 5,000th significance level. And the reason the significance level is so small is that we would like to minimize the chance of incorrectly identifying cancer causes. Okay, so in this example, I want to start by just underlining the claim, test the claim that cell phone users develop brain cancer at a higher rate than the general population. So this is the population I'm studying in this example, and is the population of cell phone users. And we're looking at the proportion. So that's what we mean here by rate. We're looking at the proportion that develop brain cancer. Okay, so the very first step here when we conduct a formal hypothesis test is to state the null and the alternative hypotheses. So if I go back and I read the claim is that cell phone users develop brain cancer at a rate higher than the general population. So this is a claim about a proportion P. So I'm going to be careful to state what P represents. Now, my null hypothesis is that is the claim that nothing is going on. This same old holds. The status quo holds, and that would just be the commonly believed proportion of 34 thousandths of a percent. So that the proportion of cell phone users who develop brain cancer is 0.00034. So I've just written that as a decimal. The alternative hypothesis, and that's what we see in the claim here, is that cell phone users develop brain cancer at a higher rate. So that is P is greater than 0.00034. And notice that the alternative hypothesis is like it's a challenge to the null hypothesis. One other thing we can see with the alternative hypothesis is it tells us that this is a right-tailed test, what some people call right-tailed test. And that's because of the greater than symbol. And that will help us in the future calculate the p-value. So we're going to be calculating an area that looks like this later on in the problem. One last thing I want to do before we move on is I want to calculate p hat, which is the sample proportion. And that was found to be in the sample 172 over 420,019 of the cell phone users develop brain cancer. And so that is about 0.0004095, 052, and it keeps going. So I wanted to point out that this number, although it's very small, it is actually larger, right, than what we see in the null hypothesis here, because there's a 3 in the 10,000th place here, and we've got a 4, which shows us in the sample the rate was higher, okay? But the question is it high enough that we believe that this statement is true for the whole entire population of cell phone users? Or is it simply higher in the sample compared to our null hypothesis? So that is the main question. In the second step of the hypothesis test, I am going to just check the requirements for the methods that we're going to be using from the textbook. This would also be the step where you would collect your sample and gather your data, which has already been done for us. So we're going to just be checking the requirements and calculating the test statistic. So the first thing with the requirements, since we're testing a claim about a proportion, we mainly need to check that we are working with a random sample. So we have a simple random sample. And we also check that we have enough like successes and failures. So that's just NP, which is approximately n times the null proportion, 42.8, and that's greater than 10, so that checks out. And we also need to check the NQ, which is about n. So we just check these two conditions, and those conditions are met, so we know that the distribution of sample proportions is approximately normal. And we can continue with the techniques from this module. So the next thing we'll do is we'll calculate the test statistic. Okay, and just so you have I'm going to draw a little sketch so you have a little idea of exactly what we're doing. So imagine that this is the sampling distribution of all possible sample proportions, right? So we're assuming that the null hypothesis is true. So that means that the mean of the distribution of sample distributions is the null value, okay? And what we would like to know is we would like to know how far apart the null value is. So that's the sort of the assumed proportion of cell phone users who have developed brain cancer. How far is our sample data, p hat, from this null value? And we know p hat was about okay, so when we calculate the test statistic, we're just calculating the z-score of our sample data, okay, in the null distribution. So of course, the mean would have a z-score of 0. So the question is, what is the z-score? This is our test statistic. Okay, and that's what we want for the test. We want to know how far apart is the null value, okay, from the sample data. How extreme is the sample data if I assume that the null hypothesis is true? So how far apart, how many standard deviations apart are these guys? So we're going to calculate the z-score of the sample data in the distribution of the sample proportions. So the z-score is given by, okay, our sample value minus the null value over the standard deviation of the null distribution. So we have, and I'm going to use a fraction here because I really want to reduce rounding since we're dealing with really tiny numbers. And I'm just going to round to 2 decimal places because I'm going to be using the standard normal table. So let's take a moment to interpret the test statistic, okay, which is just the z-score. It's basically telling me that in the null distribution, so this is the distribution of sample proportions, assuming that the null hypothesis is true, the sample data that we got, 172 divided by 420,019, This is 2.44 standard deviations above the mean, okay? So this value we see right here, the test statistic is 2.44. So these guys are fairly far apart, right? They're almost 2.5 standard deviations distance between P, my null P, and my sample data. So that's pretty far, because we remember that 2 standard deviations is usually our cutoff for unusually high or unusually low. Okay, so in step 3, we are going to be calculating what is called the p-value. Okay, and the p-value is just the area that is, it's going to just be this area, the area to the right of our test statistic. So that's really all the p-value is this red area. And how do I know that? Well, one way that you can tell is that since our alternative hypothesis had the form p is greater than 0.00034, so namely, since we had the greater than symbol, we know that this is, we know that the p-value is going to be given by the probability that a normal variable is greater than our test statistic, so 2.44. So whatever your test statistic is. Okay, and the reason we know is we know this is, you can always look at your alternative hypothesis. We see that it's greater than, and we see that this is what we would call a right-tailed test. So we're going to be calculating the area in the right tail to the right of the test statistic. So the probability that a normal random variable is greater, standard normal variable is greater than 2.4. For by symmetry, this is the same as the probability that it will be less than negative 2.44. And if you look at the standard normal table, this area is 0.0073 or 73/10,000ths. So I just want to take a moment to interpret the p-value. And remember, the p-value is just this area that you see right here. Okay, so it's the probability that the z-score is greater than 2.44. And what the p-value means is that if H naught, the null hypothesis, is true, like if we just assume that this is the true proportion of cell phone users who develop brain cancer, then there is a 73/10,000th chance, which is pretty low, of getting sample data like those observed. And when I say like, I mean a sample of size 420,019 with a sample proportion of 172 over 420,019 or larger. So step 4 of our hypothesis test is that we are just going to draw our final conclusions. And what I notice is that the p-value, which is 0.0073, is actually greater than our significance level, because we did choose it to be pretty small. And when the p-value is greater than the significance level, we do not reject the null hypothesis. Okay. And our conclusion is that there is not sufficient evidence to support the claim that cell phones cause brain cancer. Okay, so one thing to note is that you can see, although we concluded that there isn't enough evidence, that if we had just changed the significance level to a more typical 0.01 or even a 0.05, this would have changed the conclusion of our hypothesis test, right? In this case, we would have been concluding that there is some concern and there is sufficient evidence to support the claim that cell phones cause brain cancer. However, remember, to avoid making the mistake, what we'd call a type 1 error of, we decided to use a very small significance level in this case because we want to be absolutely sure before we, say that cell phones cause brain cancer. So that was the first thing I wanted to point out. The second thing I wanted to point out was something I've pointed out before. And, in the past, I've said you have to be very careful if you're going to round at any point in your calculation. My advice would have been to leave these, if possible, leave all of this in the form that it currently is and punch it into your calculator like that. So there's no rounding, only at the z-score would you round. I understand sometimes that's not possible. So I just want to say that in this case, if I was working with a really basic calculator, I would be very careful. If I was rounding at this step, I would actually make sure to go out to what is called 6 significant figures. In the past, I have said 6 decimal places is fine, but in this case, these numbers are so small. We have these leading zeros here that really don't count. They're not telling us anything significant. So instead of just 6 decimal places, I would actually go out 6 significant figures. So that actually ends up being 9 decimal places. But that's because the numbers that we're dealing with are just so tiny here. I'm going to add that special thing to use 6 significant figures for when you're working with such tiny numbers. And it's not going to happen a lot, but and then for the number and the bottom, if you have to do this calculation before taking the square root, again, you're going to get some really tiny numbers. And again, they're leading zeros. They're not significant, really. So again, if I had to round at this step, I would go out 6 significant figures. That's 12 decimal places. And then I would take the square root, and again, I'm going out those 6 significant figures, and my answer ends up being 2.4433, which rounds to 2.44. So I would get the same answer as if I had just punched this whole expression into my calculator. And so just to kind of change my previous rule, if the numbers are really tiny like this, just to be super safe, go out 6 significant figures. So in other words, just ignore these leading zeros because they're not really telling us very much.